Hello and welcome back to another video. In this problem, we're asked to prove Theorem 4, parts 3 and 5. So first we have to state what Theorem 4 actually is. And Theorem 4 states that if the functions f and g are continuous at some point a, if they're continuous at that point, and we also have c as a constant, if this is true, then we have a set of functions that are also continuous at a. And we're looking at parts 3 and 5. So parts 3 is c times the function f, and part 5 is f over g, with g of a not being equal to 0, because then we don't get into any dividing by 0 issues. So starting with part 3, we are saying that we want CF to be continuous at A. What does that mean? That means that the limit as x approaches A of CF of x is equal to CF of A. And we are going to need the fact that f and g are continuous at A. So the limit as x approaches A of f of x is equal to f of A. And we don't need g yet, but we can just write it. The limit as x approaches a of g of x is equal to g of a. Now, how do we know this? Well, this is just the definition of continuity for a function. So using it for this one, we can now use the limit laws and say, okay, we have this limit. The limit as x approaches a of c times f of x. If we have a constant within a limit, we can pull it out of the limit. So this becomes c times the limit as x approaches a of f of x. This needs to be equal to cf of a. We know that the limit as x approaches a of f of x is equal to f of a, so we can simply plug it in and get cf of a is equal to cf of a, and therefore we have proven this statement. For part b, we want the fact that the limit as x approaches a of f of x over g of x is equal to f of a over g of a, right? Again, g of a is not equal to 0, so we don't have to worry about the fact that we're using a function in a denominator or anything like that. We can simply skip to another limit law, which states that if you have the limit of a fraction, right, where we have a numerator and a denominator, that's equal to the limit of the numerator, and that is divided by the limit of the denominator. This needs to equal f of a over g of a. And in a similar way, we're just going to be plugging in from our original statements. The limit as x approaches a of f of x is equal to f of a, divided by the limit as x approaches a of g of x, we know is equal to g of a. So we have f of a divided by g over a is equal to f of a divided by g over a. And therefore, we have proved both parts 3 and 5.